Okay, so I think so. You know, we have 6 lectures this week, right? So another one is at 12 o'clock, right? Today, fine. So this is lecture number 27. So we already talked about double integral, the line integrals on reals, and so on. Today I am going to talk about complex line integrals, and you will see that how Green's theorem can be applied to obtain a one beautiful result known as Cauchy's theorem. Okay, so it's something like that: integration along a simple closed curve C, f of z dz, and this value turns out to be 0 if f of z is analytic. Okay, so this is something a nice result, and the proof depends on Cauchy's theorem. Sorry, Green's theorem. Okay, and then there's a couple of consequences of this. So I think a lot of, like, for example, you can use it. So one result is that Cauchy's theorem, if f of z is analytic inside and on a simple closed curve C, then integration along C f of z dz is 0. If the closed curve C has couple of singularities, so you can compute what is known as residues, and then in that case this integration C f of z dz turns out to be sum of those residues. Okay, so how do we compute those residues actually? So there is a formula for that. So I am going to establish this and couple of consequences of Cauchy's theorem. Okay, so first of all, complex line integral. So we take a point here, b point here. So say this is x-axis, this is y-axis. It's a complex plane, and suppose we have a curve here from A to B. So this is our some function f of z, which is continuous at all points. Okay, so f of z is a function which is given, which is continuous at all points of the curve C. Okay, so what we do? So this is the curve. We divide it into subintervals z1, z2, z3 dot dot dot, zk minus 1, zk, and so on. Finally, somewhere here zn minus 1, and so on, right? So basically we have this curve which we have divided. Okay, this is our curve C, and we are calling, so a z naught is equal to a naught and z b is equal to zn or something like that, right? And we divide it into couple of subintervals. Now if we choose a typical point xik or xik between each, so xi1, xi2, xi3 between each subinterval, so right, then I can form this sum Sn is equal to f of xi1 times z1 minus a plus f of xi2 z2 minus z1 and so on, f of xn b minus zn minus 1. So remember, I want to define the line integral along a curve C. Just we have that Riemann sum idea in our hand, right? That you compute the value of height at that function. So right, the value of the function at that point times this subinterval, right, and then we compute this sum. That's what we do. So same idea, we are copying it here. z1 minus a times, first value, second values for each xi. So basically xi1 is somewhere here. So here somewhere there is xi1, somewhere here there is xi2, and so on, right? Right, so you have all these points. I can compute this sum. Then I take the limit as n tends to infinity. That should give you something. we call it as a so we call A to be f of z dz or we sometimes also call it integration along curve C f of z dz as limit of this summation f of xi xi k times delta z k is equal to 1 to n, where limit of the largest length delta zk, okay, same thing basically what I am saying that so these are some, so delta z we call it delta z1, delta z2, delta zt, or the length of these subintervals, right? So there could be someone which is largest, right? If that goes towards 0, essentially the same thing, whole thing goes towards, the summation goes towards and goes towards infinity. When this subdivision is very, very small, this will lead to some limit, and that is nothing but integration along C f of z dz. This is the line integral, or A to B f of z dz. Okay. So you may ask, is it area, is it volume, right? So I am saying that without worrying about that physical significance, right now what we are doing, we are just copying the idea. So this is the nice thing in mathematics. We defined integration, definite integral over reals, right? A to B f of x dx. Similarly, we defined double integral over rectangle, right? Idea that similar definition we are using here, or kuch nahi kar rahe, right? Integration along C f of z dz will be this summation, right? Okay. So basically, more or less algebraic sense, I am saying that you just take the definition of in algebraic sense and take this, define this limit, and that will be the line integral, complex line integral, integration along to C f of z dz. Okay. Sometime now it may happen, this curve is basically simple closed curve. Okay. All other kind of, so we will see the implications. Now, some of the properties that I would like to say. First, sorry, this is nothing but integration along to C f of z plus integration along to C z of z dz. You can, okay, linear combination integration can be open. Integration along to C a constant times f of z dz. A is a constant, okay, that can be done. Third, A to B f of z dz minus b to a f of z dz. When you are changing the direction, actually negative sign will come. Then we have fourth property, a to b f of z dz is equal to a to, say, some point m f of z dz plus m to b f of z dz. So m is a point between a and b, right? So you can subdivide like this. So a, b and m are on C. Okay. Another very interesting property, and I love it. Actually, this property is very good. Actually, fifth one. Fifth says that mod of integration C f of z dz is less than or equal to capital M times L, where, I mean, if mod of f of z is less than m, less than or equal to m, and L is length of C. So basically you can use the definition, right, expand it, sum it, and you will get this kind of thing. I mean, this is very clear also. You see what happens if you expand the summation, right? You will see that you know, each of absolute value of the function will less than m, right? So that will quantity come as a out, right? And rest whatever left is the length of the whole curve, because those, it is some of the smaller subintervals, right? So that is the whole length. So I mean, I have asked this in many exams also, how to prove it. Okay, something not very difficult. Okay. And now you see, what is this value actually? I can just compute that f of z dz is nothing but, so if suppose f of z is nothing but u plus iv, where u and v are functions of x comma y, this is nothing but u plus iv times dx plus I times dy, right? Because dz is nothing but dx plus I times dy. So whole thing can be written as integration along c u dx minus v dy plus I times integration along c v dx plus u dy. So the complex line integral is a combination of line integral along the reals, right? I mean, right? You have seen this. We have integration along to p dx plus q dy. We can apply actually Green's theorem in both of the cases, right, to find out the further value. Here that's the thing, if f of z is analytic, remember Green's theorem can be applied. So basically if f of z is analytic actually, in that case, so conditions of Green's theorems are met, and actually you can convert this into double integral, you can convert this into double integral, and overall Cauchy-Riemann equations are satisfied, so whole thing will become 0. Okay, so I'll show you that anyway. Now before actually proceeding further on the integrals, I would like to talk about what is known as simply connected region and multiply connected region. So let us take an example. Mod z less than 2. ये मेरा सर्किल ठीक से नहीं आया है, राइट? All this region is mod z less than 2, right? Circle, right? Mod z less than 2 of radius 2, right? Circle. So circular disk, right, of radius 2. This region is known as simply connected. What do you mean by simply connected? If I take an arbitrary curve inside this region and shrink it to single point, it should not leave the region. So if I take a curve here and shrink it to single point, it will not leave this region, right? Essentially सीधे सीधे ऑटो रिक्शा वाले की भाषा में इसके अंदर कोई छेद नहीं है, राइट? अगर छेद होगा तो वो रीजन को बाहर निकल जाएगी, राइट? ये सिंपली कनेक्टेड रीजन है. Similarly, if I take this region here, ये थोड़ा सा डायग्राम ठीक नहीं आया, वो सेंटर पे होना चाहिए. आई थिंक दैट्स ऑल, इट्स ओके. सो सपोज, सो व्हाट इज दिस रीजन एक्चुअली? We can write it like 1 less than mod of z less than 2. So suppose if this is mod z is equal to 2 and internal circle is mod z is equal to 1, इन दोनों concentric circles के बीच का रीजन, इसको क्या बोलते हैं? कुएं की जगत, राइट? So this region is not simply connected. क्यों? Because if I draw a circle, suppose I draw a circle, if I draw a curve here, shrink it to single point, it will remain in the region. तो ऐसा लग रहा है कि it is simply connected. No, because if I take a curve here, shrink it to a single point, it goes outside the region, right? So this is a multiple connected region. I can take a curve here, shrink it to a single point, it goes outside. So this is multiply connected region. Right. आसान भाषा में अगर रीजन के अंदर होल्स हैं तो वो मल्टीपल कनेक्टेड है, कोई होल्स नहीं है तो सिंपली कनेक्टेड है, राइट? ओके, सो ये रीजन कैसा है, सिंपली कनेक्टेड और मल्टीपली कनेक्टेड? हाँ, मल्टीपली कनेक्टेड, राइट? बिकॉज देयर आर होल्स. Okay, now we are ready to describe the main result, which is known as Cauchy's theorem. So Cauchy was able to show this result, that integration along a simple closed curve C, f of z dz is 0 if f of z is analytic with derivative f dash of z is continuous at all points inside and on a simple closed curve C. So initially Cauchy was able to prove this, that if f of z is analytic, ये condition होनी चाहिए. Second, derivative should be continuous inside and on a simple closed curve C. कोई simple closed curve C ले ली, it could be a circle or it could be some other curve, right? Then this integral is 0. Actually later on another mathematician removed this instruction, remove this condition that derivative should be continuous. So he showed that even if only if f of z is analytic, it is fine. Then also this result holds actually. So proof was modified, right? So here actually I am going to first use Green's theorem to prove this result, which requires that derivative should be continuous. And actually I will show you how this can be done in general also, when the derivative, the continuity condition is not there. Okay, so this is the result. So proof is really simple. So f of z is equal to u plus iv is analytic and has a continuous derivative. So f dash of z will be what? Del u over del x plus I times del v over del x is equal to del v over del y minus I times del u over del y. U है, but Cauchy-Riemann equation says that del u over del x is equal to del v over del y and del v over del x is equal to minus del u over del y. These are our CR equations. F of z is analytic, so I have written the what is known, right? Derivative will be given like this and the Cauchy-Riemann equations are satisfied, and all these partial derivatives are continuous inside and on the closed curve C. Hence what we can say, that integration along C f of z dz will be integration along C u plus iv dx plus I times dy is equal to integration along C u dx minus v dy plus I times integration along C v dx plus u dy is equal to, now I can apply Green's theorem. integration along C P dx plus Q dy is equal to double integral del Q over del x minus del P over del y, if you remember that formula. So this will be minus del V over del x minus del E over del y dx dy plus I times double integral del U over del x minus del V over del y dx dy. So both are 0 using Cauchy-Riemann equations. How? Because del U over del x will be del V over del y, so this is 0, the first condition, and similarly the second condition, right? So the whole thing is 0. Such a powerful, so using Green's theorem, so that means we should know all the properties, right? So all the properties of the Green's theorems are satisfied, right? Then only we can apply this, right? So as long as f of, so here as long as f of z is analytic and the derivatives are continuous, we can get the result. Okay, so a very powerful, beautiful result, right? And I think this idea is, you know, the Cauchy theorem is so powerful result that you can see that it can be applied in variety of. So suppose you want to find the integration 0 to infinity dx over 1 minus x raised to power 6. So you can look at a complex variable function f of z जिसका real part ये integral है, apply Cauchy theorem and you can compute simply the residue and you find the value of the integral. So all beautiful applications are there. If you want to sum a series, again summation of a series can be done easily with this formula. So I am going to give you, so I mean here assumption is that there is no singularity in the region and that's why the value is 0. If there are singularities, we need to compute the residues at those singularities and then the formula is bit different. Okay, so I am going to establish that, but before that let us do Cauchy-Ghosh theorem, which is basically that removal of the condition that derivative is continuous. So this removes the restriction that f dash of z is continuous. Rest of the result remains the same. So integration along C f of z dz is 0 as long as f of z is analytic. Okay, continuity की ज़रूरत नहीं है. Okay, that is the result. So actually this proof is a bit lengthy, so what I am going to do, I will give you an outline, but I will give you an outline only for triangles. I will say that reason is triangle and how we can handle triangle, and then from there I will give you an idea how this can be generalized. Okay, so let us take a triangle. A, B and C. Suppose I take some midpoints here, E, D, F. So this is positive oriented curve, remember, when region is on the left side. So I am going to, what I am going to do actually, I am going to look at this value, integration A, B, C, A, f of z, dz. Okay, this is a triangle, our bigger triangle. A, B, C, A, right? Our simple closed curve is this triangle, bigger triangle, A, B, C, A. So I want to show that integration along C, f of z, dz is 0, right? And the condition is that f of z is analytic, that is given to us. Now I will show you that this whole integral along whole bigger triangle can be written as integral along sum of values at these smaller triangles. Okay, first I will establish that. That means पूरा triangle की वैल्यू निकालना है तो उसको हम छोटे छोटे सब ट्राइंगल्स में वैल्यू निकाल के सम करेंगे तो हमको सेम वैल्यू मिलेगी, राइट? दैट्स व्हाट आई वांट टू डू दैट. उसके लिए हम क्या करेंगे, एक पाथ यहां से ऐड करेंगे और फिर उसको रिवर्स डायरेक्शन में ऐड कर देंगे तो बेसिकली वो वैल्यू 0 हो जाएगी. सो एक इधर करेंगे, सिमिलरली इस पाथ को करेंगे, इसको करेंगे. ओके, सो दैट्स व्हाट आई एम गोइंग टू डू टू शो दैट. एंड देन व्हाट विल हैपन एक्चुअली, सो एक बार हमने ये दिखा दिया दैट होल इंटीग्रल इज सम ऑफ दिस 4 स्मॉलर triangle sum. We take the absolute value of whole thing of this bigger integral. That should be less than, who is your beautiful friend? Epsilon, right? So then you can show that, right? So थोड़ी देर पे मैं छोड़ दूंगा, but anyway let us see. So basically what I am going to do here, integration along a b c a. अभी मैं f z d z नहीं लिखूंगा क्योंकि वो तो है ही, बार बार हम लिखने की जरूरत नहीं है, राइट? तो दिस विल बी इंटीग्रेशन अलोंग d a e प्लस e b f प्लस f c d. कैन यू सी दैट? सो बेसिकली a b c a was DAE, so this portion plus EBF, this portion plus FCD, this portion, right? पूरे पाथ को हमने 3 पोर्शन में डिवाइड कर लिया, राइट? ABCA was divided into DAE, integration along DAE plus integration along EBF plus integration along FCD. करेक्ट? पूरा सर्कल, पूरा पाथ कंप्लीट हो गया. सिंपल क्लोज करो का, राइट? नाउ आई एम गोइंग टू ऐड इंटीग्रेशन अलोंग ED and minus ED. So that means I'll add integration along ED plus integration along DE. That will give us 0, right? Similarly we can do for each of them. So, okay, so I call these triangles as delta 1, delta 2, delta 3, delta 4. Delta 1, delta 2, डेल्टा 3, डेल्टा 4. इसको ऐड करेंगे तो इसको सब्ट्रैक्ट करेंगे. ओके, इसको करेंगे तो इसको रिवर्स में करेंगे, इसको करेंगे तो इसको करेंगे, राइट? ओके, सो नाउ ये 3 में ब्रेक किया. दिस इज नथिंग बट इंटीग्रेशन अलोंग DAE प्लस इंटीग्रेशन अलोंग ED. मैं ऐड करता जा रहा हूं नाउ. सो बेसिकली ED, DAE प्लस ED, एक छोटा वाला ट्राइंगल का हमने सम कर दिया, राइट? तो बचा क्या हमारे पास? समवेयर हियर इंटीग्रेशन अलोंग DE ऐड कर दिया, राइट? नाउ गो टू द नेक्स्ट वन, EBF. इसमें मैं क्या ऐड करूंगा? FE. हियर ऐड कर दिया EF प्लस integration along FCD plus DF FD. Now you can see that एक इंटीग्रल ऐड किया अगर यहां पे तो एक हमने उसका रिवर्स ऐड कर दिया बिकॉज दैट विल गिव अस 0. सिमिलरली यहां पे एक ऐड किया, उसका रिवर्स यहां पे ऐड किया. और हम क्यों ऐड कर रहे हैं? आई एम कंप्लीटिंग द स्मॉलर ट्राइंगल. सिंपल क्लोज कर्व स्मॉलर ट्राइंगल, राइट? ओके, सो अभी ये बन गया पूरा डेल्टा 1, दूसरा बन गया डेल्टा 2, तीसरा बन गया डेल्टा 3. सो एसेंशियली I can say that, note that integration along ED is same thing as minus integration along DE. Integration along FE is same thing as minus integration along EF. Integration along DF is same thing as minus integration along FD. We have used this property so that ये चार, अभी now this is one triangle, this is another triangle, this is another triangle, and this is what? A new triangle. DE, EF, FD. DE, EF, FD, बीच वाला ट्राइंगल.
DEEFFD जो रिवर्स सेट किया था ना, तो बीच वाला ट्राइंगल बन गया, राइट. सो एसेंशियली integration along the whole bigger triangle is sum of integration along the smaller triangles, right. So that means we have integration along whole A B C A is equal to integration along D A E D plus integration along E B E F EBFE, sorry, plus integration along FC DF plus integration along DEFD. So this is nothing but integration along delta 1 plus integration along delta 2 plus integration along delta 3 plus integration along delta 4. All triangle. FZ DZ सब जगह है, वो मैंने लिखा नहीं है. FZ DZ is everywhere, right. So now integration along A B C is sum of integral along AED plus EBF plus FCD plus DEF, all there, right. And you can now easily see that यहाँ पे हमने एरो इधर रखा है, उसका सिंपल क्लोज का बना, और ये वाला भी पॉजिटिव ही रहा ना, बिकॉज ऑल्सो इन दिस डायरेक्शन, राइट. सो now I can apply triangle inequality on this. So that means integration along bigger triangle f of z dz is less than or equal to mod of integration along first triangle f of z dz plus integration along second triangle f of z dz plus integration along third triangle f of z dz plus integration along delta 4 fourth triangle f of z dz, right. करेक्ट. हमने बिगर इंटीग्रल को स्मॉलर इंटीग्रल्स के सम में लिखा, राइट, स्मॉलर ट्राइंगल्स, एंड देन अप्लाई द ट्राइंगल इनइक्वालिटी. सो मॉड ऑफ z1 प्लस z2 इज लेस देन इक्वल टू मॉड ऑफ z1 प्लस मॉड ऑफ z2, राइट. अगर 5 है या 4 है, यहाँ पे 4 है, सो मॉड ऑफ z1 प्लस z2 प्लस z3 प्लस z4 इज लेस देन इक्वल टू मॉड ऑफ z1 प्लस z2 प्लस z3 प्लस सेपरेट इंडिविजुअली, राइट. Triangle inequality has been applied. Now out of these 4 triangles it may happen किसी की वैल्यू मैक्सिमम होगी, राइट. Out of these 4 values something will be maximum. So that means I can say that suppose delta 1 वाला मैक्सिमम है, so delta 2 mod will be less than equal to delta 1 mod. Similarly all other, so बाकी सारे उससे मैक्सिमम वैल्यू से कम हो गए. So that means whole I can replace all these 4 sum on the right hand side by less than equal to 4 times value of the first, right, if it is maximum, right. And there is no harm to assume that that is maximum, right. I mean ये तो खाली थिंकिंग है, राइट. एक्चुअली जो भी मैक्सिमम होगा उसको हम ले सकते हैं, दैट्स अप टू इन अवर हैंड, राइट. एक तो मैक्सिमम होगा ही, 2 मैक्सिमम है तो कोई भी ले लो, इट डजंट मैटर, राइट. ओके. So we arrive at this one. So suppose delta 1 is largest, giving largest value actually. So then in that case integration along this delta f of z dz is less than or equal to 4 times integration along delta 1 f of z dz, right, because every absolute value will be less than the maximum value, right, and if that maximum value is this, right. Now what I am going to do, see the beauty. तो ये डिवाइड करने के बाद I am able to show that the whole integration along bigger triangle is less than or equal to 4 times integration along delta 1, right. Now we can repeat the process, whatever we have done we can repeat the process for delta 1. यहाँ के मिड ट्राइंगल्स ले लिए, राइट, और फिर से बना लिया, तो we can get a similar inequality. फिर उसके अंदर फिर एक ले लिया, and we can keep on continuing, right. keep on continuing, पहला वाला उसके अंदर फिर ले लिया, right? We can, so basically I can write in general. So in general, so similarly, I am saying that we can say that delta 1 f of z dz is less than or equal to 4 times ये डेल्टा 2 है, ये वो वाला डेल्टा जो रोमन वाला है उससे डिफरेंट है, राइट? ये ट्राइंगल f of z dz. Okay, continuing in this way, I can say that dot dot integration along delta f of z, integration along delta f of z dz is less than or equal to 4 raised to power n, integration along delta n f of z dz. Right. तो ये आ गया. अब somehow you have to show that this into this is less than epsilon, right? यहीं पे ब्यूटीफुल चीज है, राइट? हाउ विल यू शो दैट द होल थिंग इज लेस देन एप्सिलॉन? तो मैं भी सोचता हूँ ये तुमको ही दे देता हूँ चाय के लिए, राइट? नाउ शो दैट. मैं हिंट तो दूंगा यहाँ पे करना क्या है, राइट? नाउ वन थिंग यू कैन अज्यूम, suppose this is our delta n triangle and there is a point z0. होगा ये z0 is a point which common. अगर इसके अंदर एक z0 पॉइंट लिया सबसे स्मॉलर ट्राइंगल डेल्टा n में, तो बिगर वाले में भी होगा, सबसे बड़े वाले में भी होगा, राइट? स्मॉलर वन. एंड आवर कंडीशन इज दैट f of z is analytic inside and on a simple closed curve C. तो इस पॉइंट पे भी एनालिटिक होगा फंक्शन, right? So now I can write down this value. Since f of z is analytic at z0, f of z can be written as f of z0 plus f dash of z0 z minus z0 plus eta times z minus z0, where for any epsilon positive we can find delta positive such that mod of eta is less than epsilon whenever mod of z minus z0 is less than delta. I think ये हमने एक बार मेंशन किया था, if you remember. So if f of z is analytic, this is satisfied. Now I am going to actually जो स्मॉलर ट्राइंगल है डेल्टा n, उसमें I will integrate this f of z. So actually now you see what could happen now. So when we evaluate, everything will be 0 except this term will remain there. Okay. So why it is that? Just think about it. Okay. Only this term is left when we actually compute this. So basically we have integration delta n f of z dz is equal to, so basically what we are doing, I am integrating this whole thing with integration along delta n in this equation, right? Eta times z minus z0 times dz. So पूरा बड़ा इंटीग्रल अब इस छोटे से ट्राइंगल के अंदर आके बस गया, राइट? Now suppose P is the perimeter of delta, then perimeter of bigger triangle, perimeter of delta n is Pn, which is P divided by 2 raised to power n. Fine. then in that case mod of z minus, कुछ चीजें अब मैं छोड़ रहा हूँ for you to verify. This is less than delta, then the whole thing is integration along this delta n f of z dz is equal to delta n eta times z minus z naught dz, whole thing is less than or equal to epsilon into p divided by 2 raised to power n into p divided by 2 raised to power n is equal to epsilon into p square divided by 4n, 4 raised to power n actually, right? So basically we have, इसमें मैंने कुछ चीज़ तुम्हारे सोचने के लिए छोड़ दिया है, right? This is less than or equal to 4 raised to power n times, bigger thing is less than or equal to epsilon times p raised to power n times 4 raised to power n is equal to epsilon into p square. Now making epsilon tends towards 0, integration along this f of z dz goes towards 0. Done. तो मैंने क्या छोड़ा, वो पेरीमीटर वाली थोड़ी सी एनालिसिस छोड़ी है सोचने के लिए तुम्हारे, राइट? थिंक ओवर इट. तो बिकॉज दिस 4 raised to power n टाइम्स ये एस्टिमेट आया है डेल्टा n के ऊपर, राइट? टाइम्स 4 raised to power n, वो कैंसिल हो गया. यू आर लेफ्ट विद p is the length of the p is the perimeter of the bigger triangle. P is fixed constant thing, right? So when you take epsilon tends to 0, the whole thing goes towards 0. Only assumption is that f of z is analytic, और कुछ हमने इसमें यूज नहीं किया, राइट? सो आई होप यू शुड बी एबल टू. तो मैंने 2-3 जगह पे तुम्हारे लिए सोचने के लिए छोड़ दिया है व्हाई इट हैपेंस, राइट? स्पेशली नंबर 1 मैं तुमको फिर बता देता हूँ कहाँ पे छोड़ा. So when we integrate this thing, integration of along delta n of f of z is this value. ये दोनों 0 होंगी, क्यों होंगी ये तुमको सोचना है, right? We are left with this eta times z minus z naught, right? And when we estimate this perimeter का idea से we have estimated that quantity and that turned out to be, so perimeter of this, ये तो सामान, I mean ठीक है, क्योंकि अगर bigger का perimeter p है, हम divide कर रहे हैं, so ये 2 raised to power n होगा. So basically whole thing, this is less than or equal to mod of eta times length of delta n, because the perimeter of delta n, you know, you remember integration along c f of z dz is mod of integration along c f of z dz is less than or equal to capital M into capital L. Capital M is upper bound and L is what? Length, or here it is the perimeter actually, because the whole thing, so that turns out to be p. Okay, so mod of z minus z naught is less than p times 2 raised to power n. Okay, so mod of eta is less than epsilon, this is p times 2 raised to power n. ये पूरा L है, L, capital L, remember in that inequality. So whole thing becomes this, making epsilon tends to 0, you are done, right? Now as soon as you establish it for triangles, you can actually do it for any other reason. Suppose there is a closed polygon, something like this, forget about this, A, B, C, D, E, F, closed polygon. We can prove the same thing for closed polygon. How? You decompose it into triangles, right? So this is this direction, this direction, this direction, this direction, this direction, this direction. So basically the idea is the whole polygon can be decomposed into smaller triangles. Triangles के लिए show कर लिया है. So basically पूरे polygon will be some of these smaller, you know, you can say that when we integrate along whole polygon is same thing as integrating along each of these triangles, some of each of these triangles, right? Similar idea, you know, everything is similar, right? And then you have to do things. I am not doing any of those things, I am giving you an idea. So this can be done actually, right? So in this direction, in this direction, in this direction, in this direction, right, right. So you can do it for this. Similarly, एक बार polygon के लिए हो गया, so then I can do it for any curve. Suppose there is a curve like this, simple closed curve C. So I can take, say, Z0 is equal to Zn, Z1, Z2, Z3, okay, at some point. So essentially what I am saying that you can do something like this, right? This, oh sorry, right. So basically this is a kind of polygon. I am saying that I can now, if I want to along for this curve, I can always divide the, so I can always find certain points on the curve so that the whole curve can be, you know, covered by this kind of polygon, right? And remember, when we subdivision is small, you can actually get the whole thing, right? So this is this kind of thing you can do. Polygon के लिए हमने show कर दिया है, so इसका मतलब curve के लिए भी हो जाएगा the same way, right? So we can do it for any simple closed curve C. एक बार इसके लिए हो गया, then we can also do it for multiply connected region. So suppose this is C1, this is C2. By making a cross cut here, H, A, B, C, maybe D, E, F, G, I, J. So here you integrate for the whole thing, then you cross cut के along आप एक इस direction में जाओ और वापस जाओ, and again curve the second. Okay, so you can traverse the path by decomposing, by making this cross cut actually. Okay, so you can do it for multiple connected region also. Okay, so हाँ हो गया अभी, that's all. ठीक है, so I will stop here. So at 12 we are going to meet and we will continue a bit further. I think complex कल तक खत्म हो जाएगा. Then we will start differential equations. Okay.